here, over here. Okay, so the first thing we need to do is wrap up our tree representations, and hopefully you'll understand why we're going about this way. Representations. Okay, so how do we get the question here, right, is we have this idea of using an array that keeps track of its parents for a binary tree, right? And does it make sense why this works? With a binary tree, why keeping track of all parents makes sense here? Yeah.
So we know if it's in the right spot, right? It has to be.
Yeah, but how can we do it in an array? Like, why does it make sense to do this in an array? So our other choices here, right? These were ways that I wanted to sit down, but not going to happen. Okay. So these are ways that we can represent trees. So what is this? Where did we use this?
That was the disjoint sets, right?
This was not disjoint set. This was just our binary search tree. Like our map is this, because what does our map do? Our binary search tree. What's that?
Key value pairs.
Key value pairs, right? And then what did we have for each node? What did we have for each node?
Like a child or a parent.
Not a child.
0, 1, and 2.
No. For our binary search tree.
Think of right in the left.
What's that?
Right in the left.
Yeah, right and a left. So within our node, right, within each node for our binary search tree, we had a right and a left pointer. Right, so sort of ignore the middle pointer here. So if we go to our binary search tree, right, we have a private nested class in here. Right here are node classes, and each node has a right and a left value, right? So when we think about what a node is, right, a node has a key and a value and a right and a left, right? So that's this. That's this structure right here. Ignore the middle. I wish he hadn't put in some sort of third node here. So just ignore this middle piece, right? We have a W, we have a right and a left pointer. They go to these things, okay? Two other alternative ways of doing this would be to have a pointer from the box just to an array that kept track of children, okay? And we sort of looked at why this would make sense for a priority queue, because what do we need to do with our priority queue? We go back, what are the key pieces of a priority queue, since a few of you weren't here last class? Right? One more time? Well, get your hand, first of all, when you guys talk, get your hands out of your mouth. If you talk with your hand, like you guys tend to, a few of you have a tendency to do this, speak. Well, no, what are the properties of a priority queue? Or a heap, I'm sorry, of a heap.
Smallest,
Yeah, so each node has to be greater than its children. That's it. There's no other like right, left, just you have to be greater than your children, okay? Of course, we're all greater than our children, but right? Okay, sorry, what?
I thought it was the other way around.
Sorry, less than, sorry, I'm thinking of a min heap, a max heap, right? So a min heap, a max heap would have it's greater than your children. A min heap is you're less than your children, right? Okay. And what else? There's only one other property of a min heap.
Oh, everything has to be like the left.
To the left, right? So when we add something to this thing, where would we add it?
Right.
Yeah, we'd add it right here. And so if we think about sort of that structure, this would lend itself pretty well, because where do I know that I've got to look? What would I do to figure out where that would be with this structure?
Like the X, like X is.
At the beginning of wherever the array is empty, I'd go through that array. I'd go into the array and I'd say, where is it empty? That's where I'm going to put this thing. Does that make sense? Because as soon as I get into one of these arrays, I go down this side, I check all the arrays. As soon as I hit something that's empty, that's where I'm going to put the thing. Yeah.
Is there like issue between one picture sheet and two? Like shouldn't the X.
So here.
Oh yeah, shouldn't X and Z both have like 2 pictures?
Nope, that's the whole point, is that W has a box that points to an array. All this is in here is a pointer to an array. So each right here
Oh, that makes sense.
is an array, and it's three things. And every single one of these is gonna have an array of three things. It doesn't matter if they're full or not. Each one of these pointers is going to be an array to three things. Again, there shouldn't be three children, it should be two things, right? But you get the idea, okay? And then lastly, we had this slightly weird one, but it is this with the array attached, but then W is just going to point to its children, and X then has a pointer to its children, but then a pointer to its siblings. This too would give a fairly easy way, because now we just go to X. Does X have a sibling? If it doesn't, that's where we're going, right? And you could iterate through that way. So it's still not great. So we come up with this idea of saying, okay, what's the simplest way to represent a tree? Okay, and the simplest way to represent a tree is to stick all of the keys into an array and then simply have an array of parents. And this we did see this with disjoint sets. This is what we did with disjoint sets, okay? But it lends, with a binary tree, it makes things super, super simple, right? Because if we think about, and again, I would not use a zero here, right? So if we think about this thing, I've got W. What is W in this tree? It's the root. So I'd say -1 here, or I'd say that it's size 1, right? So I do something different here, but that's okay. And then what's one's parent? 0, 2's parent, 0, 3's parent, 0, right? So if I look here and I say, okay, what's K's parent? K's parent is itself, it's 0. What is E's parent? K, which is 0. So 1's parent is 0. 2's parent is 0. And let's go all the way down and let's look at, well, if I ask you what M's parent is, right? M is 11. I go here, I say M's parent is P. I go up here to 5. 5 is P. Now we can make this even simpler. And this was sort of one thing I asked you to think about going into homework. How can I make this even simpler? If I think about how I get to a parent, and Donald, you sort of gave it away. How do I get to a parent, right? So if we're going to store just the keys in the array, I can do this now. I can simplify it to just this, right? So if we have to have a complete tree, we have to make sure that everything's pushed over to the left, right? In that sense, it's complete. So there's no empty holes in here with like, I'm missing an R or I'm missing a J, because that would screw things up, okay? So complete means what in this case?
Everything, all of this missing on the bottom, and everything's to the left.
You got it. So the only holes are in the bottom and everything's pushed to the left. That's complete, okay? So if we write a parent method, okay, so we got a swim method. Remember we talked about the fact that when we add something to a min heap, right, it has to swim up or swim down if it's not in the right place, okay? So we've got the swim method, and what it's saying is that, okay, if the keys at index parent K is greater than keys at K, we're going to swap, right, and swim the parent. What would a parent K method look like? How do I get the parent of one of these things? In other words, if I come in here and I say, oh, Y, what's Y's parent? What's Y's parent? So it's V. So Y is at 6, V is at 2. Mathematically, how do I get there? Divide by 3? Well, what if I come to 2? What's 2's parent?
Okay.
2's parent is K. If I divide by 3, that's not going to quite work.
By 2.
If I divide by 2, so let's see if I go Y. There's Y. 6 to here. 6 divided by 2 is 3. That takes me to B.
Wait, divided by 2 minus 1.
Divide by 2 minus 1. Close. Minus 1 divided by 2. right? Okay, so if I think about getting from any child to its parent in this array, if I subtract 1, 5, and divide by 2, now what do I get?
It's integers, right? So it truncates down to.
Yeah. So 5 divided by 2 is 2, and y's parent is v. Now what's y's other child? It's p, right? So y gave me 5 divided by 2. What does this give me? Also 2, because it's,
So you don't.
you do.
Oh,
I mean,
5
5 minus 1 divided by
4 over 2 is 2.
It's still right. We still do, we want to make this, sorry, always the same. We don't want to like have it, if it's odd, we do this, if it's even, we don't do it, right? So we just say we always, these two numbers, sorry, these two numbers, p and y, right? If you subtract 1 and divide by 2, you're always going to get 2. This is the beauty of floor division. Okay, so I come way out here and I say, oh, 12 and 13, right? No, sorry, 11 and 12. 11 and 12, right? What's the parent?
5.
5. So I take either one and I subtract 1, I'm going to get 10 or 11. I divide by 2, I get 5, I get p. Okay. Does that make sense? So that's it. So to do this, we simply need this method that gives us a parent. Super easy. Now, how do I get from a parent to a child? Yeah, you inverse the operation. Right? And it will give us our left and right child. Now, do we have to do 2 chunks of math here? Yeah, now we do have to account for the right and left child, right? Depending on how we are looking for things. Okay. Now, the nice thing about this is, where am I going? Like, where should I in the tree, just looking at the tree structure, where should I put something? Right to Y, right? This is where I would add another element to this thing. And where does it go? Where does it go in our data structure, underlying data structure? Just stick it at the end of the array and we're done. Now, what if we have to swim? What do we do? Or what are we comparing it to? Parent, which is just, right? If I put it in at 14, let's say I put in Z at 14. I say, actually, let's say I put in A, B. I'm not looking at the actual numbers here. Let's say A, B, we don't have a C. Let's say I stick C in here. What do I have to do with the C? Is C in the right place? We gotta think that maybe I should be using numbers here. It's a Wednesday morning. Right, so C is presumably not in the right place because it is, what would I want to compare it to first? Its parent. What's its parent?
That's at 14.
Yep.
So parent is 6.
Its parent is 6. Look at that. We come back to our thing. We look at that. Its parent is 6. It's Y. So I say, okay, compare C to its parent, 6. Is C greater than or less than Y? Less than. So should it swap? Yeah, we swap, right? Because it's a min heap. We want the minimum things at the top. So we swap. Now what do I do with C? Compare it to its parent, which is what? 2, which is V. Is it smaller than V? So what do? I keep swimming. I swap, right? And then I compare it to K, because V's parent is K, and do I swap? Yep, so it swims right to the top. Okay, so this structure makes the underlying methods really pretty easy. Okay, if we went in and tried to do that with any one of these other structures, is it going to be reasonably difficult? Like, how do we find the empty space to put things in? Yeah, you're going to have to traverse the whole tree. So if I say, like, this is it, how would I find the empty spot in this tree? Given our binary search tree, we've just got a right and a left pointer. How would I find it?
Since you want it to be like everything to the left, when we start to the left, and then check if it's.
I mean,
But at the end of the list, that should be fine.
no, we're not doing a list. What I'm saying is that if I use this structure, our binary search tree structure, how do I know where to put it?
Check if
B?
Or
Is that what you said?
don't we have to go through each one?
I don't know any other way than going through every single node until I say, does this thing have no children? Does this thing have no children? Does this thing have no children? Does like, or does like, right? Because otherwise, if any one of these had one child, then I'd be down that way until you get to something that only has one child or no children. And then, but you have to keep track of the level too. Because let's say this didn't have a child. I can't just ask, do you not have any children? Because these all don't have any children, but then neither does this. Then where do I put it? So I'd have to keep track of the level that we were at, like how many steps down we've gone, the depth with the depth. Yeah, we'd have to keep track of the depth. And then whether we had two children, whether we had no children, like it would be really, really messy. Whereas this structure right here, we stick it at the end. One real quick thing that is a lot of people do, some people do, which is what would make this even slightly easier, and it maybe mathematically it will make it simpler here. What would make life easier for us mathematically in this array? Look at this bottom one and think about what would make life easier. Well, I'll ask you a slightly different question. What do you notice about that array? What's kind of odd about the array?
It's like two.
Increases numerically, yes. What? Pairs.
Like 1, 1, 2, 2.
No, but do they all do that? What's wrong with it?
Oh,
We've got 3 zeros. So what should we do? What would make life easy and nice mathematically?
The first year.
How would you -2 and then?
Negative-
-1,
negative,
-2, -1.
Okay. Other thoughts?
negative how many?
Well, we talked about that. That would, yeah, if we stuck in like how many, like how big the total thing was. Okay. What else would make this easier mathematically, specifically? Someone said it, but just didn't run with it. Well, what is this? Why are we starting at 0 here? Yeah, but why are we starting at 0? Because that's where an array starts. Does it make sense to start at 0 in this structure? Let's think about mathematically what happens if we start at 1. In other words, we just get rid, like we just say, hey, that's empty. Okay, we could keep track of the size of the array in there, but we're not going to use it. Yep. We just say, hey, that thing's empty. Now what happens for each one of these things, right? 12 and 13, right? What's my root of 12 and 13 now? Well, 12 and 13 go to 6. So what do I have to do to get there? Just divide by 2. I don't have to worry about the -1, right? So all I do, right, if I get to go that direction, my parent is just divide by 2. My left child is times 2. My right child is times 2 plus 1. Right? Because when we do it, our children here, what's the math to get to a child here? Let's go from, I don't know, B. How do I get from B to my children? Right, we're at 3 times 2. Well, from 3 to 7 is times 2 plus 1 and times 2 plus 2, right? Times 2 plus 1 and times 2 plus 2 to get to children, when what we can do is simply say, hey, why don't we just do times 2 and times 2 plus 1? It's just mathematically cleaner. The algorithm, the Princeton textbook does this math. A lot of people prefer to do this just because it makes things much easier. And there's nothing to say you can't. What do I lose here? Like why, what's the only issue with this? Yes, I'm using the memory for 1 memory box extra. No, not at all. And the other thing is you just got to make sure you keep track of the math in your head and you don't start using 0 for some reason, right? You don't iterate through like I equals 0. Well, don't start at 0 because you don't have a 0 there. Okay. So this makes it much, much simpler to get from your children to your parent and from your parent to your children. Okay, so that's priority queues. So we base our priority queue off of which of these data structures? No, we use the heap, right? Because what? It's as fast as a binary search tree for add and for remove smallest,
Yes.
but get smallest is O1. Why? Because it's right on the top, right? It's always the top thing. So get smallest is always going to be the fastest thing. So for certain, and again, priority queues don't get a lot of love, right? They're not super useful for as many things as a binary search tree. But they, a priority queue based off of a heap is really, really useful for certain things, okay? And the heap login time is amoritized. We might have some resizes. So that's one issue again, but we've talked about that sort of across the board with our anything that's array backed. The other issue is what can't binary search trees do? What's the one thing that binary search trees are not good at? Or actually just really can't do? One more time here. Duplicates. Yeah, we can't have duplicates in a binary search tree because we're comparing, right? What do we know about our keys in a binary search tree? Or if it's a set, hash set, right? Or sorry, not tree set or
They're distinct.
they're distinct. They have to be distinct values, right? So we can't do duplicates with the binary search tree. So a heap allows us to do that. Okay. And array-based heaps take less memory than representing the tree as nodes with right and left pointers. Okay, so that's super helpful. And then this is just the interface for it. And we could allow for different orders. So we could have a min PQ, we could have a max PQ. And we have to have, what's the one thing we have to have with a priority queue though? What are we making an assumption about our data? It doesn't necessarily need to be, I mean, that's where it works really well. What do we have to know about our data? Say that we would know in a binary search tree, but that we wouldn't necessarily know in a hash map.
Oh, how much data? Like the fixed size of the priority?
That's, again, that's super helpful, but this one is sort of structurally inherent. Not close. What does that also mean? If I can sort something, then I have to be able to comparable. They have to be able to, you have to be able to compare the objects in one of these things, right? I can't have priority. I can't have the smallest thing if I can't determine what smaller means, right? So, yeah, so you have to have that. Okay. Okay. This is it. We're done with data structures, more or less. We're not done with underlying data structures. Then we sort of put them together. So, abstract data structures. We've got lists, right? We can add, we can, or insert, depending on how we're doing it. We can get, we retrieve by the index. We have our map with our key value pairs. We can get the key, and we retrieve by calling the key. We have sets, similar to maps. We can add the key. We can do contains key. And again, we retrieve by that key identity. Priority queues, we add, we can get the smallest. And that way we retrieve by key order. So we're always grabbing the, if it's a min PQ, the smallest thing. Our disjoint sets, we're just looking at whether or not two things are connected. We can check if they're connected, or we can connect two things. We can check if they're connected. And we simply look at those two values to look at those, whether or not those things have happened. Okay. So we've covered a lot of them. These are all sorts of different types of collections. Okay, so we have double-ended priority queues, we have queues, we have lists, we have maps, we have priority queues, queues, sets, disjoint sets, and stack. This is directly from, where do we think this is from? I think this is like the overall structuring of pretty much every data structure in Java. So we have arrays. We haven't ever talked about bit arrays or circular buffers, but we have hash tables, hash to trace, a sparse array, which is not something we really talked about, linked lists, skip lists. Again, we haven't looked at XOR linked lists, but most of these should at least be like, oh yeah, I sort of have a general sense of what that is talking about, right? Some of them are way more obscure than others, but we have B trees, binary search trees. There's our red-black tree, heaps, R trees. We haven't really talked about that. Tries, we haven't also talked about. If you really want to check out tries, you can do that in LeetCode. And then we start to get into graphs. Okay. Questions on priority queues or why did those all disappear? That's so interesting. So he laid this out. So we've got different set and map implementations, right? We really didn't talk about sort of linear programming or chaining. Chaining is what we did for our hash sets, right? We had linked lists in each bucket. Okay, there's other ways of doing that. Linked lists, binary search trees, black trees, or red black trees, B trees. We've got heaps. Our priority queues, different ways of this is the interface, and then these are implementations. List interface. We have linked list and an array list. Disjoint sets, different ways of implementing those. So is there any questions, first of all, on heaps or binary search or heaps or priority queues? Yeah.
Not really the way that you determine if something's like left for them, but the way that you replace, like in your min queue. I'm just thinking about like the children and like how you structure that.
Yep. Okay. So now we understand. So what's going to be the underlying backing structure of this thing? It's a heap. What's going to be the underlying backing structure now? An array, right? And the first item in the array in spot 1 theoretically would be what? 1. And then so we'd have something like, I don't really want to draw out the whole thing. 1, 3, 1, 6, 5, 5, 3. I didn't make it long enough, right? So it would just be an array of all these things, right? And I can go and I can say, okay, you know, this, if I divide by 2, I get this. I come out here 5, I divide by 2, I get 1, right? So you have the whole structure in an array. Okay. So where would I add something to this thing?
To the number 5, probably.
So here?
Or, yeah, that one.
Yeah, I would. But let's say I'm adding 2. If I'm adding 7, would I have any issues? Is it in the right place? It's in the right place. But if I add 2, what do I have to do?
Push the you have to reorganize everything.
I have to I don't have to reorganize everything. I can be real careful because I put something in the right place. That's where I want it to go. So I'm just going to add it to the end of the array. I'm going to be like, hey, it goes on the end of the array. I just start swimming. So that's the code we just saw where it said parent, right? So I say, hey, I'm going to look at your parent. How do I find the parent? I call the parent method, which does what mathematically? Just divides by 2. No, remember, I'm starting at 1. So all I have to do is divide by 2, right? So I divide by 2. I compare it to this. Is it smaller than this? I swap. Now 5's here, 2's here. Then what do I do? Compare it to its parent, divide by 2. I look at this thing, whatever is in this index. It's 1. Is it bigger? Nope, I'm done.
So you leave it on the left side?
So 2 would be here.
Yeah.
5 would be here, and I'm done. Because again, the only properties of a heap are that the children are less, parent is less than the children. And everything's pushed to the right side. So by putting this here, everything's pushed as far left as so it's complete. Right? That's why I put it there. But then by swapping up here, all I have to do is make sure that I don't care if this could be 1 here. I don't care that 2 is what its relationship is to its children or what its relationship to anything over here is.
And this thing can have, well, I'm looking at it, so it has duplicates in it.
Yep, can have duplicates.
Okay, sounds good.
Yep. And then to remove, Okay, the only trick with remove is if I remove small, because what's the only operations I can do with this thing? Right, I don't really want to scroll really fast, but I'll scroll really fast. But basically, with a heap or with a heap, what am I interacting with? The smallest. I only care about the small. The whole point of this thing is it's a priority queue, right? So I can add whatever I want. So I've got to add, but then I can look at the smallest or I can remove the smallest. I can return the smallest or so what I'm only interacting with is this thing. So I remove what goes away. 3 goes away. Right? Now that's problematic because this should be up here, but I can't slide this up here because then my tree is no longer complete. I swap it with 8. I say, hey, I'm going to remove the smallest. I take the last thing in the tree, and where would I grab this from in my array? It's the last thing in the array. It's super simple. I grab the last thing in the array. I swap it. So 8 comes up here. This goes away. Then what do? I swim down. I say, okay, look at my children. Okay, which one of these is smaller? And am I bigger than that? So first of all, I could do it a couple different ways, right? Obviously the code gets a little bit convoluted in my ors and ands here, but whatever. I'm gonna compare it to both these things. This is the smaller, I'm bigger than that. I'm gonna swap 3 and 8. So 3 comes up, 8 comes down. Then I do the same thing here. 8 will end up here, 5, and my 3. Still complete, right? I've pulled from I've removed from the right place, and I've maintained my heap properties. Cool. Okay. So what that leads us to is graphs and traversals. Graphs are super cool. Where do we see graphs? Let's think about it. Everywhere. What do you mean everywhere? For what?
Like presentations to people to.
But like, so give me an example of something that is a graph.
A bar graph, a pie chart.
Nope, sorry, different. Okay.
Sorry.
Nope, that's okay. Now, no, I'm realizing, and I almost said this a second ago. So yes, right. So when we think about graphs, we might think about a bar graph, or like would a pie chart be a graph from data science? Yeah, no, like a pie chart. Isn't that a graph? I mean, theoretically, we call it a graph, right? A line graph. We call it a line graph. We're changing up the definition. So a graph in data science is a little bit different. So let's start there because you actually asked the question last class as well. Because yes, right, we could call anything that has a graphic a graph, right? But we're gonna switch up the definition in this class at least. Okay, so what is a tree, first of all? What is a tree? So we got nodes connected by edges, and what's sort of a rule about those nodes connected by edges? So if let's
0, 1, or 2.
Well, could I have 3 and still have it be a tree?
Oh yeah, normal tree, not BSC.
Right, so a binary tree looks something like this. Is that a binary tree? Sure. Is it a complete binary tree?
No.
No, it's not complete. This thing's in the wrong place, but it's still a tree. We could have, theoretically, I could do that. That's still a tree.
You
Right?
can't have circular connections, like that bottom node can't connect back.
This can't come back up here like this. Or
Yeah,
this, right? I can't do that, right? So we can't have, and how might we phrase that? A loop. In other words, how many ways can I get from one node to another? In a loop, but in a tree, can I get from one node to another in more than one way?
no.
No, that's it. That's sort of the definition. I can only get from one node to another through one path. This is a tree, because to get from here to here, I can only go this way. If I put in this connection, now I can go this way or this way. No longer a tree. That's the only definition of a tree. Nodes and vertices with one path, okay? So we have a set of nodes, a set of edges, exactly one path between the two nodes. So this is a tree, Yep, this. Yep. No, no. Okay, because those last two, there's more than one way to get from one node to another. Okay. Put this in slideshow mode here. Okay, a root. So now we're going to get some definitions, and then there's going to be a fair amount of them. I apologize for. Okay, a rooted tree is a tree where we've chosen one node as the root. We've talked about that before. Every node n except the root has exactly one parent. Can't have more than one parent. Right? Slightly different than real life. Defined as the first node on the path from n to the root. So if I come here, I know that C's parent is B. Okay, and we're done. Okay, a node with no child is a leaf. Okay, so this all should be review. Okay, we have a host of different types of trees. Like we've seen this one. Where'd this one come from? Yep, that's our disjoint sets. Is that a tree? What did I just do? Hang on, okay. That's a tree. These are all different types of trees, right? And we're not really putting any stipulations on a tree except those two things: nodes and edges, one path. Okay. The interesting thing is that these are also, we sort of think about trees sort of generically in here, but anytime you look at an organizational chart, like we could do this for the school. Who's at the top of the organizational chart for Stevenson School? Dr. Griffiths, he's the president. Who's under Dr. Griffiths? You may not all know this. Miss Bates, actually, Mrs. Bates, and the head of the primary school. There's two heads down there, right? So there's a head of a middle school and a head of lower school. Those three people are under Dr. Griffiths. And then you'd have, like, then it gets really messy, all right? Because we'd have Miss Gladden underneath Miss Bates. Who else would be under Miss Bates? Koshi, right? But then you start to look at different, like, sometimes I'm not quite sure where people fall, right? So you have that whole organizational chart. Is that a tree? No, not sort of. It's a tree, right? Because you don't have like loops where like, oh yeah, Dr. Griffiths is in charge of Miss Bates, but Miss Bates is also in charge of Dr. Griffiths. No, it doesn't happen that way, right? You have direct reports above you. You might have a lot of direct reports above you, right? Theoretically, my bosses are Climo, right? Mix Gladden, Miss Stockdale. Like theoretically, I have like all sorts of incoming heads, but it's not circular, right? Oh, in a place like this, it could be circular.
Yeah,
Like, so Climo and I'm trying to think of like Miss Stockdale and Climo. Miss Stockdale is a coach under Climo, but theoretically Climo is a residential faculty under Miss Stockdale. I don't know if that would be circular because it wouldn't be in the same, would it be in the same org chart?
That's like academics versus.
Yeah, you'd have an athletic one that came down from Climo to Stockdale, but then you'd have a residential one that went from Stockdale to Climo.
So it's still a valid tree.
It's still a valid tree if you separated it out that way. Didn't really mean to go into that philosophical little tangent, but what's that?
you know, this stock, the other one, coach stock.
Yeah, I guess you could differentiate by title, right? Because in a place like this, yeah, okay. We have manual, so this is a training manual for the management of malaria, right? So does this person have a fever? Okay, are they under the age of 5? If they are, do this. If they aren't, do this, right? This is sort of a flow graph of what you do in training for malaria, okay? Your family lineage, right? So if you look at your family tree, is that a tree?
Yeah.
It hopefully is, right? Yes. Are there cases where it might not be? Yes, but no, hopefully all of our trees are family trees. Okay. Have you guys ever heard the song, I'm My Own Grandpa? It's really funny. I'm my own grandpa. Never mind. It's a really goofy song. You can't, but it's fun.
Your own friend.
You can't, but it's funny. If you listen to it, it makes sense, but yeah. Okay, so tree iteration. I'm not going to go through this whole spiel because we've actually gone through tree iteration. It's called tree traversal. Okay, and when we think about doing this, does anyone remember doing this in LeetCode specifically? We did it for our binary search tree in terms of printing it,
Oh, we took out the center, and then took out the center of that each side. And that's-
right? It was our recursive method that traversed and then printed in different places. Is that ringing any bells? Like we print, then we recursively call left and right, or we call left and then print and then call right. How about when I drew the picture? Remember when I drew the circle around this thing?
Yeah.
And we listed the things as we went around that's what we're talking about now, okay? So we can do tree traversal in a whole bunch of different ways. So there is level order. What do we think the level order would do for us? By tier. So what would print first? D, B, F, A, C, E, G. That's what we get there. So that's level order, right? And this could be one way we kept track of what level we're on when we're going down through a tree. We could do that. So that is level order. And then there's 3 depth first traversals. And this is going to be really important carrying into graphs. So the reason we're talking about it again is because these types of traversals are going to be important for that. Okay. So we have pre-order, in order, and post-order. Okay. And we're going deep into the node. So we go depth first. The reason is because if we think about level order, the term we're going to use in a graph is breadth first search. So I look at this level, then I check its children, and then I check all of those children. So I'm checking by breadth. A depth first search goes down all the way into one spot in the node and then starts working its way back out. Okay. And then traversing a node is different than visiting a node. We'll deal with that as we start implementing these things. So pre-order, we're going to try and think through this. Oh, we got time. So if our node is null, we return. Otherwise, we're going to print the key. We're going to pre-order on the left and then pre-order on the right. What happens here? I want you to write down on your piece of paper, given pre-order, how this is going to print. We're starting at the root. We always start at the root. So how is it going to print? Write down your answer. You need a pencil to write down your answer. Well, we know what's going to be first. D, because immediately as soon as I step into it, I print the key. D is not null, I print the key. I'll give you that one. While you're doing that, you need to update one thing. Anyone got an answer? Okay, so we print D, then we pre-order left. So where do we go? B, then what do we do? Okay. Why do we go all the way down this way and then to C?
It's recursive and the first thing you hit is left, so you go all the way down to the left.
Yep.
But it hits, there's nothing there, so it hits null, then you go to the one that's before that, the B, and then you go B dot right.
Okay.
You go
And
to
then-
B
Okay, we're back to D,
dot
right? F, E, G. Does everyone agree on that one? Okay. Okay, put that right in the middle. Okay, so D, B, A, C, F, E, G. Okay. Here, I'm gonna do this and then it's gonna, we'll do that. Okay, how about in order? Give a try for that one. So all we've done in the code, right? This is what we did in the lead code. All you do, what do you move? You just move where the print statement is, right? That's it. We're always going left first and then right. And then this is where we put the print statement for the key. Okay, so what first? Hey, yeah, because we're gonna go left. If we think about walking through this code, we go in order left, right? So we come here. Okay? And then
Again,
what's that?
Get it again.
Yeah, right, so in order, sorry, not null, we call in order left, we go left. Okay, we continue to go left until we get to A, we finally print it, then what?
And go back to B.
Yeah, we come back up, we print B, then we finally hit this statement, right? We go down, we print C, come back up. Now, D,
It's just in order.
it's in order, it's literally in order, right? Is this useful? Specifically for what type of tree is this really good for? A binary search tree, because what do we know about these things this way? They're in order. So it's a really nice way to print a binary search tree because it's going to give you them in order, right? With other types of trees, with a heap, is it gonna make any difference? No, the only thing we know is that the smallest thing will be here. That's really all we know in terms of our in order. Which would be a better way of printing a heap, actually? Which one of these would be best? I didn't, what's that? I'd say the pre-order, yeah, because we go from the top down to the left, or maybe level order, because you know that each node is going to be,
Does level order go from left to right too?
no, remember level order goes top to bottom.
I know, but when it goes to the bottom, since there's two children, does it print? It prints.
It'll always print left and then right.
Yeah, so then.
Yeah.
If it doesn't print anything, we put something there. Yeah.
Oh, you could think about it that way too, but it has to if it's a heap, right? So. Okay, that's in order, and then finally we just have our right, that's BC, we know that, we did that. Okay, and then finally post order. What do we think post order does? Think about what it does here. So it goes through, right? We get left, right, and then print. This one's kind of tricky.
Omit.
No, it will print everything. But it's hard to wrap your head around sort of recursively in terms of the call stack. Right, because it seems like, what does it seem like it should not print? A, right? Because it comes down here and then it seems to backtrack, and then the first thing you'd expect it to print is what? C or maybe B, right? We'll see in a second how, like, an easy way to figure this out, okay? It is A, C, B, E, G, F, D.
Oh, it goes from the left side, then to the right side, then to the right.
Yeah, it goes all the way down to the left, then to the right, right? Then prints those things, then comes back up, does the same thing on the left side, and finally comes back.
Is that better for a heap? Because you're comparing, in a heap, you don't care about the character.
Yeah.
Because you like return, so that means you're like out of it, right?
No, only if X is null. The D return. Right? So you got to think of this as a recursive call stack, and that's where this gets confusing. I can build it in a thing and we'll look at it. But if you think of it as a recursive call stack, these things are getting added and then printed into the recursive call stack. This is the most confusing one, I think, just because you've got a host of things that are printing after the fact. But I will show you the trick here. So we underline this thing, okay? If we make a path around this, it becomes pretty straightforward because our pre-order traversal, does he go through all of these? I thought he went through all of them. No, okay. So our pre-order traversal is, again, what would our pre-order traversal be? 1, yeah, so essentially, if you look at the picture, we just add them every time we pass to the left of the node. We draw a circle, we pass to the left, add it. Add it. Pass to the left, add it, come up, add it, add it, add it. That makes sense? So it's every time we pass to the left. Our in order traversal, when do we add them? In this way. Obviously, the computer can't figure this out. This is just for us to figure it out. 4 first, right? So when we pass underneath is our in order. I pass underneath, I had 4, then 2, 7, 5, 8, 1, 3, and that would be in order, right? If we thought of this as a binary search tree, that would be in order. This is clearly not a binary search tree. What is this actually? It's a heap. Yep. Is it a heap? It's close to a heap. It's got a problem.
Because
It's not complete. Yeah.
To the under it, cause like you go 4, but you don't add 2 after adding, it's under it, but. isn't
You
it
do.
to the right?
No. What do you mean?
Cause you said 7, 5, 8.
Yep.
And it's 4, 7, 8, 5.
It's 4, 2, 7, 5, 8, 1, 3. That would be in order. Again, it doesn't work as nicely for this one because it's not sequential. It's not a binary search tree. But that would be in order. And then post order, this is where I think it makes this the easiest. What are we going to assume about post order? When we pass where? To the right. So we come down, post order, we hit 4, 7, 8, 5, 2. You just sort of work your way back up. Then we go all the way back down to 9, 6, 3, and then 1. That's the post order. And again, it's in many respects sort of the most confusing one. Okay, but it's the way the recursive call stack gets put in. Do we have a general sense of this? Other than maybe a little bit of head scratching around the post order. Okay. Okay. And then like, why do we have all these different tree traversals? Well, we saw in order. What's in order good for with a binary search tree? Printing it in order, right? This is pre-order. And if you think about the way that your computer folders are laid out, this is the way your computer folders are laid out. Yeah. I mean, old style computers are like, has anyone ever seen this type of structure? Nobody? Okay. This is sort of the underlying structure of your computer. Okay. If I go into my computer, yeah. So if I go into my terminal, you won't see it quite that way unless I really stretch. But like, okay, these are all my files. And then I could go in and say, okay, well, what's in my documents folder? And I can say, all right, CD. Yep. And then I can list everything in my documents folder, and it's going to give me all these things, right? And I could go in and I could, if there's a folder inside of that, I could go into the folder inside of that. Okay. So what this does is essentially is given that this is just a post order traversal of this thing. But what it does is it lays out your, come on. Oh, why did that? Why did I get my bar back? Okay. What it does is, okay, I'm going to put in this file, and then I go through, and if I think about my pre-order, right, it's going to add the direct overlay, and then under direct overlay, it's going to have this file with these two things in it, right? So we can see that this structure follows that. And then in direct overlay also is direct 0 and direct 0 SLN. And then I come back up and over underneath, also underneath this is notes, and then Python with that. right? So it lays it out in a way that a file folder would be laid out. So that's pre-order. Post-order traversal for getting sizes of files. So if I want to know all the sizes of these things, I'd use post-order, because if I'm adding up, if I want to know what size of folders are in DirectIO, what do I need to have?
What is every one size of folders?
Like how much memory, like how many, let's just assume how many documents are in each one of these things. Let's just assume that's what it is.
Let's go with the loss.
Well, you have to, if I drew that big picture around, what do I want to add first? To get here, what do I have to add up?
The GX.
The two at the bottom. So I have to come down below here. I'm drawing my big picture around this thing. I have to get this and this, that adds up to this. Right? And then I come around and to get to this, what do I have to add up? This and this and this. Got it. And then I come back over here. This is alone. But to get this full size up here, I have to add this and this. This comes up to this, and I get the whole thing. Okay? So that would be a use of post-order traversal, working from the bottom up, adding up our file sizes. Okay, I know I'm sort of spraying with a fire hose here, and I apologize. I did want to get through more of graphs for us. Okay, here we go. We're finally definitions of trees. Trees are really good for, like we talked about, hierarchical relationships, like an org chart for a company, right? Not so good for all sorts of other things. So this is an example. It's the Paris Metro station, right? Is it a tree? Why not? Multiple connections. I can get from B to A. How many different ways do we think we get from B to A? Probably a lot. Right? There are lots and lots of different ways to get from VA. If I looked at just one of these things, are these trees? Just the little sections?
Spindly ones. But
Yeah, these are trees. But the whole thing is not. Because again, I can get from B to A a whole bunch of different ways. I've got cycles in there. So a tree is a set of nodes and edges, can only have one path. A graph, and this is our definition of a graph in computer science class, especially talking about data structures and algorithms. We got a set of nodes, a set of 0 or more edges which connect two nodes, and that's it. Okay. There's one stipulation here that we'll throw in for the types of graphs that we're going to be using. All trees are graphs, not all graphs are trees. This is a graph. This is a tree, but also a graph. Graph.
So then isn't like everything would be graph?
Yep. Well, everything that has nodes with connections, set of nodes and connectors.
it's like the square.
Literally everything.
No, it's trees and graphs. There's all sorts of things that are not graphs.
This is like the square rectangle relationship, like,
Yes,
okay.
right? But no, there's lots of things that aren't graphs, but anything with nodes and edges is a graph, theoretically.
Wait, the first one, the graph?
Yep. Well, actually, what is this? Two graphs, two disconnected graphs. I've got a graph here and a graph here, because I can have 0 edges. I don't have to have any edges to make it a graph. It's 2.
There's a-
Yep. Okay. The trick with, okay, this is just fun. Is this a tree or a graph? It's definitely a graph. Is it a tree? Why not? What makes it not a tree? What?
Oh, the orange one that you put, right?
Where? Here?
Yeah.
This?
Yeah.
No.
Or like to get, like Antonich to.
Oh,
Right.
Dublin, Pleasanton, right? Isn't that?
No.
It connects around.
No. All of these, everything out here, these are all trees. Because is there only one way to get from one place to another? If I'm trying to get from Dublin to North San Jose, Is there more than one way to get there other than going from here to here?
Yeah,
There is? What?
you go further back, right?
That's not a loop, though. That's just going deeper into a tree. That's like saying I can go 3 layers up the tree and come back down the tree, and that's a different thing. It's not,
Okay.
right? Mary, what was it?
No.
That's a loop. I can get from San Bruno to Millbrae this way or that way. I have 2 different ways of getting there. If I took that off, is it a tree? It is. Okay, but
No,
that
but-
little loop, excuse me?
San Jose.
Nope. There's no other way. If I had a ferry from here to here, sure, but there's no way. There's only one way to get from here to anywhere else on this map, other than that. I mean, what Ethan's saying is true. I could go like this, or I could go like this, but that doesn't make it not a tree. That's like saying, I'm gonna get from here to here. There's this way to go, but there's also this way to go.
Oh, it's still in the tree.
It's still in the tree. You're just adding stuff to it. Right? Okay. Okay, that's that. We're going to almost exclusively be using simple graphs. And what a simple graph means is that we have no connections to ourselves. We have none of these little loops, and we don't have double connections. Okay, so no parallel edges and no vertexes or edges that connect a vertex to itself. So our simple graph is this, not those 2. All of our graphs will be simple. And when we say graph, that's what we mean. So now, where do we see graphs? Now that we have a definition of graphs, where do we see graphs? Where do you use graphs in your everyday life? Maps. Anytime you pull up a map, you're basing it, it's all based off of graph theory, right? So you're trying to find directions to anywhere, there's underlying graphs. That's what mapping GPS uses. What else? Sure, maze would be, right? If there's any sort of circular, it could be a tree, right? But it probably is a graph. Come on. A tree is a graph, so anytime we're using a tree, but let's think of practical places. What are like every day?
Like the streets.
Paris Metro, so that's maps. The BART's a map, street's a map. Come on, think broader. What, sorry? Oh, pipes, like pipes. Yeah, pipes would be, yeah, it'd be a graph, like you'd have to, like when you were designing the water system, it would be, yeah, it'd be a graph. Right, because you could have circular, right, water comes from one place, goes to another, yeah. Electrical would be. What do you mean?
Like in soccer and basketball, they'll show you like, oh, where the players shot.
All the passes, yeah, all the passes, like a pass chart, right, still there. What do you all spend all your time on? Not necessarily all of you. Social media. Guess what? That's a graph. Think about what social media is.
Gives you a path, like.
One way.
They're nodes. We're all nodes. And we have connections to other people. Are there circular connections? If we follow each other, or if we both follow someone else, right? Or if I follow 2 people away, right?
I thought we couldn't have circular.
We can't have connections to ourselves. I'm not a friend to myself,
Oh.
right? I haven't followed myself. I followed you, you have followed Mary, Mary's followed me, whatever. That's a circle,
Yeah.
but there's no parallel connections. Like I don't follow Mary and Mary following me. That's one connection, not 2,
Yeah.
right?
Oh.
So all social media is also a graph. Real quickly, I just want to get through this. We have directed graphs and undirected graphs. In other words, in this case, like I can follow Mary and Mary doesn't follow me. That's a directed graph. Okay. In some sort of undirected, like a map, if we have directions, like I can get to San Jose and I can get back from San Jose on the same road, right? That's undirected. We can have weights. for our edges, which we're gonna spend a fair amount of time with. And then we can have cyclic or acyclical graphs. A cyclical graph is I can get from A to where? To A. I can go around in a circle. Either one of these is cyclical. This is acyclical because if I go out of A, can I get back?
No.
No, I can only go from A to C, from C to D. I can't go anywhere from D. It's not cyclical, acyclical. There's no cycle in it that I can travel. Ouch. Okay. Also acyclical because this is theoretically,
You can get, you could go from.
I can go from A to B, right? I can go from B to E. I can't get back to A, so there's no cycle in there. Well, I mean, I can travel the same path, but I can't travel a distinct path back to A. All right, everybody, have an awesome rest of your day. What day of the week is it? Yikes, how is it only Wednesday? Okay, anyone else not here on Friday for APs? Oh, yeah, track and, okay. Yeah, this week is just, the next 2 weeks are just messy.
I don't think Alex will be here on Friday as well. Safety.
Okay.